All right, this lesson is about features of exponential graphs and how to graph graphs when they are in exponential form and what kind of things we need to know about those graphs. So the first thing that we need to recognize is what an exponential function looks like, and that typically looks like y equals a times b to the x power. Sometimes it also has a plus or minus c on the end, but not always. So when you have b is greater than 1, you were talking about 1.1 and higher, then you have an increasing function. And it is called exponential growth because it is going to be growing, and you'll see that when we do the graphs. If you have b is less than 1, that function is decreasing. However, this less than 1 doesn't mean negative. It means between, so 0 up to 1. So you're talking about fractions and decimals that are in proper form. So like 1/3, 2/3, 0.75, 0.888, things like that. Now, if you had like something, say, that was 7/2, which is an improper fraction, that one actually would result in an increasing or a growth function because 7/2 is the same as 3.5, which is greater than 1. So be careful about this. Just recognize that this does not mean negative. So these are not negatives. That's not what we're talking about. And when they are decreasing, this is called exponential decay. And so there's lots of examples in the real world of exponential growth and decay. When you're talking about viruses, you're talking about exponential growth. When you're talking about, like if you buy a car, as soon as you buy the car, the value starts going down. So that would be exponential decay. Our vocabulary word for this section is asymptote, and that is the line which graphs get close to but never touch or cross. So these are like a boundary line for your graph, and you can't go past them when you are graphing them. So notice the directions say that we're going to use the graphing calculator to put these into the table. So I'm going to go ahead, well, that was unnecessary. I'm going to go ahead and pull up the calculator, and that way we will have it ready. So I'm going to use the calculator first to fill in the table. So you're just going to go to y equals, clear out anything that's there, and then do 2 caret, so that's the button above the division, and x. You've got to use the caret for it to make the x go into the exponent spot. Otherwise, you're going to just have 2x, which is going to give you a line, not an exponential graph. So make sure that you put it in the exponent spot. I'm going to go ahead and graph it so we can see what it will look like. So I do have this zoomed in to where y goes from -1 to 10, and x goes from -10 to 10. So that way it's just focused on those two top quadrants, quadrant 1 and quadrant 2, because that's where all of this graph is taking place. And you can see where that boundary line is. You can see that it does not go below the x-axis, and so that is a result of that asymptote. So if we go and look at the table, so think about the graph as getting, as the numbers go more and more positive, the y values also are going more and more positive. So if we look at this table, as we get into these bigger and bigger numbers, these numbers are getting huge. Like this one that's highlighted, when x is 28, y is over 200 million. So these numbers get big really, really fast. They also get really, really small. And so you can see here 0 is 1, and then they start getting closer and closer to y equals 0. but they actually never become y equals 0. This one, in fact, is a scientific notation that would be a very small decimal close to 0. So that's why that looks a little bit different. For our purposes, we're going to use the middle of the table. Usually -2 to 2 will suffice. You just want to be sure and include that 0 so that you have your y-intercept. So on my table, I'm going to have -2 and 0.25, and I will let you use decimals. They are allowed this time. 0, 1, 1, 2, and 2, 4. So what an exponential function is saying is let's multiply by 2 every time our x goes up. So think about when you go from when you go from 0.25, you multiply by 2, you're going to get 0.5. Multiply by 2 again, and you're going to get 1. 1 times 2 is 2. 2 times 2 is 4. So that's what is happening in an exponential function. And so we can graph this. -2 is going to be very close to 0, but not touching it. -1 is going to be at a half. 0 is at 1. 1 goes up to 2, and 2 goes up to 4. And so you can see that curve developing. So the way we draw this, think about being on a roller coaster, and you get on where it's flat, and it's flat for a second, and then it starts going up a hill. And it just goes up and up that hill. So that's kind of what our situation is here. So we can answer these questions about this. Of course, we could answer that this is growth without even seeing the graph. Obviously, the graph shows us that it is growing, but because it was greater than 1, b was greater than 1, then we know also that it's growth. The asymptote, again, is that boundary, and so you can see that boundary happening right here where y equals 0, and so that's how we write our asymptote. The domain of these is going to be all real numbers, much like a parabola was. The range of this is based on the asymptote. So because our asymptote is at 0, our range is everything greater than 0. So we have y is greater than 0. And then the y-intercept is something that you can easily get from either the graph or the table, because it happens where x is 0. So x is 0, y is 1, so the y-intercept is 0, 1. That's it. You're done. So let's go down here and do number 2, and we're going to kind of compare how these two relate to each other, since this one is going to be a decay. So it's got a fraction in there for b, so we already know that that's going to be decay. You don't even have to work it out to know that. So when we go to y equals, we're going to clear this out, and then we're going to do in parentheses 1 divided by 2. That's just the easiest way to do it. And then caret x. So just make sure your 1 divided by 2 is in parentheses, or it'll try to put the x on just the 2, and we do not want that. So when we graph this one, you can see that it's coming down. It is decaying. It starts out on the left up really high, and then it's going to go down and get flat at 0. So if we look at this table, it's the opposite of the other one. See, these negative numbers are now really, really big. And as we go down, after we pass 0, we're getting closer and closer to y being 0 without ever touching 0. So again, we can use -2 to 2. So we're going to have -2, 4, -1, 2, 0, 1, 1.5, and 2 is 0.25. And you can see that the numbers are the same as the ones in the table above it, but they go the opposite direction. That's because now, instead of multiplying by 2 each time, we're dividing by 2. 4 divided by 2 is 2. 2 divided by 2 is 1. 1 divided by 2 is 1/2. 1/2 divided by 2 is 1/4. So that's what that means for this problem. So when we get ready to graph this, we're going to do 2, so left 2 and then up 4, and then negative 1, 2, 0, 1, 1 goes with half, and 2 goes with 0.25. And so you can see this is going to start up here and then curve and flatten out. So this is like the end of the roller coaster where it comes back into the thing where you can get off and it gets flat so that you can get off. And so you can see these curves are mirror images of each other. If you could fold this paper in half on a mirror, that's what you would get. You would get those images. So since this one has a boundary, again at 0, we have an asymptote of 0. Domain is again all real numbers. Range is again y is greater than 0, and that's because the entire graph is up here above 0. So that's not going to change just because the graph changed directions. And then the y-intercept is again 0, 1. So actually the only thing that changed on this one, the only thing that 1/2 did was change the direction of the graph and make it a decay instead of growth. All the other attributes stay the same. Asymptote, domain, range, y-intercept, everything is the same. On the next page, we do add some more complex situations. So when you're going to do one like this, you have to do 2 caret x, and then you have to use the right arrow button to get back down out of the exponent so that you can do -3. If you forgot to do that, if you did 2 caret x and then just did -3, notice the -3 stays up there with the x, which is not at all what you want. So make sure that you're using this right arrow button to get out of the exponent before you do any addition or subtraction. All right, so this graph, oh, this looks different. It goes down below. So I'm going to have to reset this window, and you can see that this one goes down to a boundary of -3. So when we make this table, our numbers are going to be different. So you can see as we get like more and more negative, that those are becoming closer and closer to -3. And you can see that they're not quite -3. Like if you click on one of them, it's -2.999999403953552. So they're not really -3, but they're so close that the calculator does just do that. And when that happens, when you just get the same number like that over and over, that's your asymptote. That's what it's getting to that it can't really touch. And so you can see here as we go into the positive numbers that these numbers are going up really fast and they're getting really big. So we're going to focus again on the middle area around the 0. So we're going to have -2 and -2.75, -1 and -2.5, 0 and -2, 1 and -1, and 2 and 1. So those are the numbers that we're going to put on the graph. Now remember when you're counting down that this is -1, -2, -3, and that -2.75, so I've gone over to -2 and now I've got to go down to 2.75. That's all the way down here almost to the 3. So be really careful when you're doing this that you're putting those points in the right place, because we're not used to plotting points that aren't on an intersection on the grid. So then the next one is going to be up just a little bit, and then the next one is going to be 0, -2, and then we move into these whole numbers like this. And you can see the next number would have been 3, 5. That would have been the next pair. And so you can add that. You can actually have as many numbers in the table as you want, but 5 needs to be your minimum. So if you want to do more numbers, if it'll make you feel more confident in your graph, you can definitely add another pair. So that would be like, extending the table, so to speak. All right, so then when we graph this, we're going to be flat, 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 and then we're going to turn and start going up, and then we're going to start going up. Oh man, I messed it up. And then we're going to, at this point, when we get to 2, 1, we're going to start going up really steep. So that's when the exponential part really kicks in, is right here. The pen was trying to make that a straight line. So obviously this had a whole number here. This is going to be growth. The asymptote this time though is y equals -3 because that boundary has now been moved down here to -3. So we have to keep that in mind. Domain is still all real numbers, but the range has changed too. Now the range is everything greater than -3. So that range will change if your asymptote changes. And then the y-intercept this time is just 0, -2. And you, again, can see that from both the graph and the table. So make sure that you're getting that right. All right, the next one, this one's got a fraction. So that means that we hopefully know that that fraction is going to give us a decay model. And so we're going to type that in, clear this out. When I type this in, I'm just going to do 1 divided by 4 in parentheses, caret x, and then use my right arrow button so that I can put +1 down beside of it and not up in the exponent. When we look at this graph, we can see it's decaying. Starts on the left up high, and then it comes in and flattens out to the right. So that means a decay model. We're going to look at the table, and you can see that these are really big numbers. Like this one is almost 300 million. So these negative numbers are the big ones this time. Then when we come in after we have x is 0, then you can see they start going towards 1, but they never really make it to 1. And you can see all these repeated 1s means that's our boundary. So we're going to do on here -2, 17, -1, 5, 0, 2, 1, and 1.25, and 2, 1.0625. And you don't have to write out a big long number. You can round that off to 1.06. It doesn't matter. So notice that our first one is 17. We cannot put 17 on here. That would be way up in the other graph above it. So we're just going to skip that one. Leave it in your table. It's fine. And we're going to start at -1, 5 because that's what we can put on our graph. And then we've got 0, 2. And then the next one is 1 and 1.25. So that's right above the 1, not below it. The next one is 2 and 1.0265. So that's, again, close, close, close to the 1, but not touching it. So this one is going to have a sharp turn, comes in really straight, and then it flattens out really quickly, especially compared to the one above it that has a nice gradual curve. This one's much sharper. Now, this one has an asymptote of y equals 1 because you can see that boundary right here has been moved up to 1. So the domain, all real numbers, range is now y is greater than 1 because that's where our boundary line is, and the entire graph is up above that boundary line, so that's why it's greater than, because they are literally greater than that line. And this time our y-intercept is 0, 2, and you can see that both here and here. Okay, so you might be thinking, or maybe you figured it out, what caused the asymptote to move? Well, the key to the asymptote is if something is added or subtracted. What that means is you have that basic curve, and then when you say -3, it literally takes the curve and just moves it down 3. It moved the boundary from 0 to -3. Then on the other one, you had a plus 1. So that boundary got shifted up 1. So that's literally what causes it. So I want us to write on here that adding or subtracting moves the asymptote. Okay, so that's the only difference in these two and the two on the other side. That's why it's not y equals 0 when you're asked to identify it, because it's got this plus or this minus. Now, number 5 does not have a plus or minus. That means the asymptote is going to remain at 0. The 4 at the beginning is an A. We have not had one with an A yet, but this one does have an A, and that changes it in a different way. What that makes it do is it makes it get taller more quickly. So you'll see that because we're going to be able to compare 4 times 1/2 to the x power to this previous one where we just did regular 1/2 to the x power. So let's go ahead and type this in so we can get our table. So you want to just do 4 parentheses 1 divided by 2 and then caret x so that it literally looks like it looks on the paper. When we look at the graph, you can probably already see that that's a tighter turn. It's going up a little bit faster. It doesn't spread out as much as this one that we drew. Whoops. Then if we look at the table, we're going to get slightly different numbers. So this time, instead of using -2 because it's 16, I'm going to move down and I am going to actually use -1 first. So I'm going to use -1, 0, 1, 2, and 3 instead of -2 to +2. The reason that I'm doing that is because I can't put 16 on my graph, and I kind of need 3 and 0.5 because that's going to show me, that's going to like set me up to make my curve into a flat line at the x-axis. So I'm going to have 8, which I also can't put on the graph, but we're still going to keep it 4, 2, 1, and then 0.5. And then you can see the next one is going to be 0.25 and so on, because this 1/2, remember, means we're dividing by 2. 8 divided by 4 is 2, 4 divided by 2 is 2, 2 divided by 2 is 1, and so on. So that's why that's going to work. All right, so -1, 8, that would actually be right about here. So I'm going to go ahead and put that on that other line, just so that we have something to help us draw this curve more successfully. And then 0, 4 is way up at the top also. And then 1, 2, and then 2, 1, and then 3.5 is right here. And if you look at the next one, it's 4 and then 0.25, so that would be even further down. But notice we never pass 0. We never have a negative number show up. So I drew that extra one on there. You don't have to do that. So we're going to start up here and curve, and it's a nice gentle curve. It's not sharp like the one above it, but it does change up who is matched up according to your tables. So I'm going to leave the calculator up there. We'll use that table. And so look at this. So -2 in our original problem before we had 4 was 4. Or before we multiplied by 4 is what I meant. So we had -2 with 4. Now we've got -2 with 16. Then we had -1 with 2. Now we have -1 with 8. Before, our y-intercept was 0, 1. Now it's 0, 4. So this entire situation has been bumped up by a factor of 4. That's why it got so much taller than the other one. So this one is a decay. It had a fraction. So we're looking at this number always. Remember, B is boss to decide if it's growth or decay. This number does not determine that. Just the number with, like, right beside of the x. So that's decay. This asymptote is back at 0 because we didn't have a plus or a minus. Our domain is still all real numbers. Our range is y is greater than 0 because that's everything in the graph is above the x-axis. And this time our y-intercept is 0, 4. Okay, so it just is the same kind of picture or graph over and over, but with slight differences. Maybe you spread it out. Maybe you make it skinnier. Maybe you move it up. Maybe you move it down. But the shape does not change. A decay is always going to look like this scoop. And a growth is always going to look like you're just going up a mountain. Okay? So hopefully we can be successful with this.